Margie! Aunt Margie!
Alex! You're here! I'm so excited to see you.
I'm here, but why'd you want me to meet you here?
You're going to love this. Allow me to introduce you to my newest invention. The Margie 2, or M2 for short.
Whoa!
M2, this is Alex.
Hello, Alex. It is a pleasure to meet you.
It's nice to meet you too, Margie too.
What do you think?
What is it?
It is a research vessel designed to collect information from severe storms.
Can this thing fly?
M2 is not a thing. She is a highly advanced, fully functional artificial intelligence capable of reasoning and logic. And yes, Alex, she can fly.
How does it fly? I don't see a propeller or anything.
Well, she is designed with a proprietary solar cell inertia engine.
A proprietary what? Solar cell? She's solar powered?
That's better. And yes, she is absolutely fully solar powered. The sun is a fully sustainable, vastly untapped source of energy. M2 is the first prototype of her kind. She's not fully operational yet. But when she is, she'll be able to fly through the most dangerous of storms and gather very valuable information. That information will further our understanding of the most severe storms and may even lead to more accurate predictions in the future.
What kind of severe storms?
Let me show you. M2, would you be a sweetie and cue up the promotional video for Alex and play it through your external projectors?
Certainly. Queuing up promotional video. Activating external projector.
Have you ever been caught in a severe storm? A thunderstorm? A blizzard? A tornado? Or even a hurricane? Severe storms can cause massive damage to homes and the environment. Every year, trees are torn from the ground and thrown around by high-speed winds. Hail the size of golf balls harm natural wildlife, break windows, and can even dent cars. Tornadoes flatten towns, and cities are flooded when hurricanes cause rivers to overflow and levees to break. Severe storms can also affect travel. They make it unsafe to drive or fly. Every year, airline flights are delayed, canceled, or grounded. We must understand these weather patterns in order to live safely within them. Most scientists expect global climate change to make extreme weather events more common in the near future. So the more we know about these severe weather conditions, the better prepared we can be. The M2 is a state-of-the-art, highly advanced solar-powered research vessel that will revolutionize how severe storms are studied. By smoothly flying within the destructive forces of these natural phenomena, the M2 can collect valuable data that until now has been beyond reach. This precious data will further science's understanding of these destructive forces of nature and will significantly change the way meteorologists are able to forecast these violent storms. Designed by famed scientist and inventor Margie Lopez, the M2 is indeed the research vessel of the future. Paid for by the Margie Lopez Science Research Foundation and a generous contribution from the California Institute for Biodiversity.
That's great! Can Margie 2 really do all of that?
Affirmative.
Well, not quite yet. If I were to take her out in a hurricane right now, she'd be coming home in pieces. So, I think for now, we would be safer exploring local weather conditions. Once we figure out how the simplest of weather conditions are formed, we will be well on our way to figuring out how the more severe and dangerous storms are formed.
But how am I supposed to learn about something as large and dangerous as a hurricane on such a beautiful day?
I'll tell you what. Before we get to that, I have something for you.
What's this?
It's something I put together just for you. It's a digital notebook full of fun scientific facts. I've already uploaded a bunch of really great stuff on there for you to check out.
Excellent!
Ooh, do you feel that?
Feel what? The wind?
Yeah, the wind! We may not have a hurricane up close and personal to study, not that you would want one, but the processes that make a simple wind blow are the same processes that form severe weather conditions, like hurricanes and tornadoes.
What makes the wind blow?
For every great story, there's a beginning, and the same goes for the answer to your question. Everything that has to do with the wind or the weather starts there.
What does the sun have to do with hurricanes and tornadoes? Why is it so important? Find this out and more next time in Heat Things Up. Last time, Alex joined his Aunt Margie for the launch of her newest invention, the M2, a state-of-the-art prototype research vessel. Margie explained to Alex that M2 was created to pilot through extreme storms and collect important information to further understanding of these phenomena. Alex was overjoyed that he was going to be able to study these violent and exciting storms, but was left curious as to how that was going to happen, considering there wasn't any sign of storms to be found. Margie explained to Alex that to learn about extreme storms, all he had to do was to study the wind, and that all weather on Earth started with the sun. And so, our story continues in Heat Things Up.
The sun?
That's right, the sun.
What does the sun have to do with anything?
The sun may be 93 million miles away, but it's the cause of all weather on the planet Earth. It's also the cause of a lot of other things, like keeping you warm and growing your food, for starters. Just about all the energy in our atmosphere comes from the sun. Solar energy travels through the vacuum of space as waves in the form of electromagnetic radiation.
Electromagnetic radiation, the direct transfer of energy through space by waves made up of charged particles.
Before reaching the Earth, the sun's radiation must first pass through our atmosphere. The atmosphere absorbs some of this radiation, but not all of it. Most of the radiation that does go through our atmosphere is either absorbed or reflected back into space. The energy that is absorbed, however, heats Earth's surface unequally. This is probably the most important thing to remember when we talk about the weather.
So the sun's electromagnetic radiation is the cause of extreme storms?
Well, like I said, the unequal heating of the Earth's surface through radiation is the most important part of the equation, but not the only part. Next, heat has to transfer back into the atmosphere.
Transfer? How?
Heat is transferred in 3 ways. M2?
Yes, Margie.
How about you tell us what they are?
It would be my pleasure. The first type of heat transfer is conduction, the transfer of heat in solids by the vibration of molecules. The second type of heat transfer is convection, the transfer of heat in fluids by the movement of heated material. The third type of heat transfer is radiation, the direct transfer of heat energy by waves made up of charged particles.
Outstanding work, M2.
Thank you.
Now that M2 has told us what the 3 types of heat transfer are, let's take a closer look.
Whoa, she is just full of gadgets.
Instruments and tools, yes. Gadgets, no. Remember, she is a research vessel. And what good is a research vessel if you can't do tests and experiments in the field, right? Anyway, have you ever seen a boiling pot of water?
Sure.
Well, it's the perfect way to show you practical examples of all three types of heat transfer in action. Let's take a look. As the hot plate heats up, what do you think will happen?
Well, the hot plate will get really hot, heating up the pot, which will make the water boil.
Good! That process of heat traveling from the hot plate to the pot is called conduction.
Conduction.
What was that?
What?
That large booming voice. Who was that? Where did it come from?
Honestly, I have no idea. He kind of seems to follow me around everywhere. I try to ignore it and stick to the science.
Okay?
As I was saying, the process of heat traveling from the hot plate to the pot is called conduction. At a molecular level, the heat transferring into the pot from the hot plate is causing the molecules in the bottom of the solid pot to vibrate. As the molecules begin to vibrate faster, they cause their neighboring molecules to also vibrate at a rapid pace. This continues until the entire pot becomes heated and every molecule is vibrating at a rapid speed.
So conduction is the transfer of heat between two molecules that are touching?
You're close. The molecules have to vibrate at a rapid pace and cause their neighboring molecules to also vibrate.
So a good example of conduction would be
Exactly! The vibrating molecules from the hot object cause the molecules in your hand to also vibrate at a rapid pace, causing your fingers to burn.
I probably shouldn't do that then, huh?
Probably not a good idea, no. So you got conduction. Now let's talk about heat transfer process numero dos.
Convection.
How does he know what you're going to say?
What? Oh, I'm not sure. It's not important. Let's look at the water in the pot. What do you see?
There are tiny little air bubbles rising up from the bottom of the pot.
Good! Why do you think that is?
The heat from the pot causes the water at the bottom to boil. That's what those little bubbles are.
Those little bubbles are vaporized water. So what do you think happens to the space occupied by that bubble after it rises?
More water takes its place?
Exactly. Because the water vapor bubbles are lighter than the rest of the surrounding water, they float to the top, and cooler water sinks to take its place. This flow of warmer, rising water vapor and cooler, sinking water causes a current that repeats until the water boils. So, convection, or convection current, is the process of heating molecules in any fluid by the upward and downward movement of heat. Understand?
I think so. It's a lot like...
Absolutely! Great example! Okay, so we've already talked a little about the last type of heat transfer.
radiation!
Hey, that's my line.
That's right, radiation. Objects that are hot, like this pot of boiling water, give off or radiate heat. This process is called radiation. The pot in this demonstration can be compared to the sun since both radiate heat. The sun's rays heat the earth, and the boiling water heats the air above it. Can you think of an example of radiation?
Let me think. How about
Not really. That's more conduction. That's a good example of convection, but not radiation. Yes, great example of radiation. Another example would be if you were to go to the beach on a warm and beautiful summer day and lay out in the sun. The heat that you would feel on your body is the sun's radiation. How are you doing so far? Of course! Which part would you like me to explain again? Conduction, convection, radiation, unequal heating. Great! Let's set up a few examples of the 3 types of heat transfer and see if you can identify them. Touching something hot is... Standing outside of the beach is... Boiling water is... Heating a house is... Heating a piece of metal in a flame is... Wow! Great job! Now that you're familiar with heat transfer, let's look at how it applies to our atmosphere. First thing, air is a really poor conductor of heat. As solar energy breaks through the atmosphere, it warms the land and sea. That heat is transferred to a shallow layer of air a few centimeters thick, just above it, through the process of conduction.
So it's a lot like the hot plate in the pot. Only this time the hot plate's the Earth's surface, and the pot is the thin layer of air above it.
That's a good observation. In fact, what happens next is also similar to the pot of water. That shallow layer of warm air above the surface rises, leaving a void behind to be filled. Cooler air from above sinks in to fill that void. That air is also heated and rises, causing a convection current. This current is the major way that heat is transferred in the troposphere. Let's take a look at another example. Something a little different. Ah! Here it is!
What is it?
This is our next experiment. A remote-controlled miniature hot air balloon. While I inflate the balloon, I'll explain how convection works in our atmosphere. Then you can take the balloon for a spin. Sound good?
Sounds excellent!
First, let's review. Heat in the form of radiation penetrates the atmosphere, warming the surface of the Earth unequally. Then the heat from the surface warms up a small layer of air just above it through conduction. This warm air rises and causes convection currents. The rising of that air is similar to how a hot air balloon rises. When the air molecules in the balloon are heated, they expand and move further from one another, causing the balloon to rise. However, when the molecules are cooled, they compress and gather closer together, and the balloon sinks.
So when the air inside the balloon is heated, it expands and causes the balloon to inflate. But at the same time, the air becomes lighter, causing the balloon to lift off the ground and rise. Right?
Right.
Then, when the air molecules inside the balloon cool down, the air becomes heavier, causing the balloon to land?
Right again. In fact, a convection current occurs inside the hot air balloon. The flame heats up the air around it, and as this air moves upward, cooler air comes in to take the place of the warm air. Then the process repeats with this new, cooler air. As long as this convection current continues, the warm, lighter air causes the balloon to rise. When the flame shuts off, the convection current goes away because the air just continually gets cooler without heating back up. And when the air inside the balloon becomes cooler and heavier than the air outside it, the balloon starts to sink. Okay, the balloon is ready. Take it for a spin!
Excellent! Excellent! All right! All right! Excellent! All right! So that's it? Heat transfer is the cause of extreme storms?
Oh, Alex,